Good morning, ladies and gentlemen. Thank you for the invitation. I am here to present our research in the area of inertial navigation for measurement while drilling applications downhole. This research has been ongoing for more than 5 years in my laboratory with the participation of my students Alex Jurkov, Justin Cloutier, and Dr. Ephraim Pecht. Up front, I would like to say that our goal is to replace the present day navigation for horizontal drilling with modern inertial navigation methods, the ones that are used in rocket science and in ground navigation routinely. I will talk about the motivation that led us to this type of research, make a review on of inertial navigation systems, and of the concept of in-drilling alignment that we developed in order to reduce the error accumulating during the inertial navigation process downhole. I will talk about the in-drilling alignment apparatus that we have designed and share some experimental results with you. This is a pending patent technology. The horizontal drilling industry today is, in our opinion, 60 to 50 years behind in terms of navigation, because it still utilizes magnetic sensors to determine the azimuth angle of the bottom hole assembly while drilling. And this is for a very good reason, because the environment downhole is very hostile. You have tremendous temperature dynamics, tremendous vibration dynamics, and you need relatively high precision when drilling because of regulatory issues, but also because more than ever we started drilling adjacent holes, and in the process we need to be very careful of the direction in which we drill. The inertial navigation system apparatus that is proposed here is based on using the so-called inertial measurement units or inertial sensors, the modern way of navigation that has enhanced tremendously our capabilities to navigate in space, in rockets, and on the ground. However, this innovation has not penetrated deep downhole for the reasons that I mentioned. We are still using the industry standard today is magnetometers and set of accelerometers to measure the angles and get the attitude information downhole. The magnetometers in particular are affected by randomly located ore deposits, magnetic interference from the drill string, which is particularly important in when drilling adjacent holes. It becomes almost prohibitive to navigate when you have adjacent holes. They're influenced, the magnetometers are insulated from magnetic interference by lengthy non-magnetic collars that are expensive and can be 30 to 50, 60 feet long. So the navigational system is located well behind the drill bit, and some near drill bit rotations go unnoticed because of that. So our motivation, as I mentioned, has been to replace this obsolete, in our opinion, navigation system with modern inertial navigation, reduce the overall cost of measurement while drilling processes, and increase the production from adjacent reservoirs by accurately controlling navigating the well bore. The inertial navigation system, modern inertial navigation system, consists of 3 mutually perpendicular accelerometers and gyroscopes, and is in a position to calculate real-time velocity and attitude by integrating acceleration, and as well as calculating real-time roll, pitch, and azimuth by integrating the rate of turn. This is an example of a tactical grade LN200 inertial measurement unit of the type that is used in Pershing rockets. In order to acquire these 2 units that we have, we had to undergo FBI clearance in order to experiment with these devices for downhole applications. The disadvantage of traditional inertial navigation systems, however, are several, and the most important is the unlimited error growth while surveying, which in the hostile environment downhole with high temperature and vibration dynamics makes the performance of these units as they are inferior to magnetometer-based navigation. For this reason, the industry never seriously introduced inertial navigation systems for horizontal drilling to this point. The reason for that is of this error accumulation is because the position and attitude are developed due to the with integration, and this integration, of course, involves also integrating the biases and the errors incorporated in the accelerometers and gyroscopes, which in a vibration environment, and if you have high temperature differences, accumulates prohibitively to precise navigation. We have developed a method that we called in-drilling alignment, which utilizes non-stationary reference measurements to reduce the estimated azimuth error. And up front, I want to tell you what it is. The drilling process, the horizontal drilling process, stops many times along the way during the operation, and we utilize these stops to introduce controlled motion in our inertial measurement unit downhole. We move it back and forth with a known acceleration, and in the process of this movement, which can also be non-linear, can be spiral-like or rotational, in this motion is completely controlled by us. It is done when the drilling process naturally stopped, and we know the acceleration and the angular velocities that we introduced. We can use, therefore, this knowledge in the real downhole environment to estimate mathematically the error that the inertial measurement unit generates at the moment, just before the drilling process starts again, and compensate for this error a process that we call in-drilling alignment.